Okay, so this is the last mechanism that you need to know in year for the AS specification, and it's the elimination or the dehydration of an alcohol. So if we have ethanol, I'll draw it out in full. So it's very similar to elimination of haloalkanes. Okay, so as ethanol, you heat it up with conch sulfuric acid. We'll have a look at how that works in a minute. And what happens is you remove water from it. So you remove the OH from that carbon, and you remove a hydrogen from the one next door. So if you eliminate ethanol, you would get ethene and water. So it's the opposite of hydration of ethene, really, which is odd because like sulfuric acid was the catalyst for the Backel reaction there as well, if you remember. Very different mechanism though. Right, let's see what happens here. Okay, so you have ethanol, and you've got some H pluses from the sulfuric acid. Now, really, if it's conch sulfuric acid, you wouldn't have H pluses, they'd be stuck onto the sulfuric. So we should show them as leaving the sulfuric, but it's absolutely fine for the purposes of the exam to show it like this. So what happens is, right, you've got a lone pair of electrons on, you've got a lone pair of electrons on, you've got two lone pairs. That acts as a base. What do bases do? They accept protons. So that's going, the pair of electrons goes onto the proton, which will actually be stuck to the sulfuric acid in reality. And so you're going to protonate the ethanol. So that will now be, all these bits don't change, do they? That's all the same. I should just make that a bit, make that bond a bit longer. And now we've got the oxygen, it's got two protons attached. One that it's picked up from the sulfuric acid there. Now that oxygen doesn't look right, does it? It's got 3 bonds. Remember, usually if you've got 3 bonds, it'll have a positive charge on it. And if you do your conservation of charge bit, remember, you've got a 1 plus and a neutral thing. So this thing has got to have a plus on it somewhere. Okay. Now, this oxygen is kind of pulls the electron density out of that bond because it's positively charged, which means it can drop off. Okay, so this, well, this goes onto there, but before that happens is, right, the pair of electrons in that bond go there to make the pi bond. So these 2 electrons, right, in the bond there, they're going to form a pi bond. So that means this hydrogen is going to come off as an H plus. Okay, so let's draw what we've got there. You'll have, we form that new pi bond. These 2 hydrogens are still stuck onto the carbon. These 2 hydrogens are still stuck on. But this one here has come off as H plus. And you will lose a water. So that bit there has come off as H2O. So you can see here, look, we've regenerated the H plus that we used up there. So the H plus is acting as a catalyst. Okay, that is all you need to know about that mechanism. Important to realize here, right, you've got a positive charge on this oxygen. That's going to withdraw charge all the way out, all the way down there, isn't it? Which makes these bonds here between this carbon and its hydrogens, makes them all a little bit weaker, and that's why that can break and the electrons go to form the pi bond. Anyway, that is the mechanism for elimination. Right, so let's talk about, I think it's practical 5A or 5B, and this is where you do this. You dehydrate an alcohol. Okay, so this is AQA required practical 5. Forget if it's 5A or 5B. So what we do is you set up a pear-shaped flask, a few anti-bumping granules in the bottom there, and you're going to heat it nice and gently. And what we've got in there is we have got they use cyclohexanol. Okay, and that's because it's quite a big alcohol. So the alkene that comes from it is going to be a liquid. You don't want to, like you did it with ethanol, the alkene you'd make would be ethene, it would just all escape, wouldn't it? You wouldn't be able to collect your product. So in there we've got cyclohexanol. And a sulfuric acid, conch sulfuric. I think it also works with conch phosphoric. Okay, I think it might be, they recommend you use conch phosphoric. So it's quite a lot of conch phosphoric you put in there. Right, and you warm it up, and this is of course your condenser. You put your water in at the bottom and out at the top, and you need a thermometer here to monitor the temperature. And that's sealed there. Right, let's just have a think. So we are going to get cyclohexanol, which is like this. And when you dehydrate that, you're going to get cyclohexene. Okay, let's have a think about the boiling points of those then. So, right, this is going to be high because it can form H bonds. This is going to be a lot lower because, it can only form van der Waals forces. Okay, so that's important because as soon as you start heating here, right, and you start dehydrating your cyclohexanol, what is going to tend to evaporate first from the surface here is not boil off. What's going to boil off? Most of the cyclohexanol will stay put. It will be more the cyclohexene coming out because it's got a lower boiling point. Cyclohexene vapor will come up here and it will start condensing there. Right, and so we're going to collect that cyclohexene vapor, really cyclohexene liquid, in a beaker there. And it won't be very pure because, it won't be very pure. It will contain some water. It will contain also some cyclohexanol. And when you collect it, you can see it separates into 2 layers. Okay, and the bottom layer is H2O, 2 immiscible liquids, and the top layer is the it's not purple, it's colorless, but the top layer is going to be cyclohexene. That's what's going to be in there. It won't mix with water because it only forms van der Waals forces, and water of course forms hydrogen bonds, but you will get some cyclohexanol in this bottom layer. Any cyclohexanol that boils over will go in the aqueous layer because that can form hydrogen bonds. So what you've got there is mostly top layer of cyclohexene and a bottom layer of some cyclohexanol. So there's some cyclohexanol will evaporate inevitably, so you when you're heating it. So you'll get that there. You carry on doing this until you never heat a flask to dryness because that's dangerous. But you carry on doing it till you haven't got you only got like that much left in or something, and then you need to then purify your cyclohexene in the next part of the practical. So let's talk about that, seeing as we're here. Right, and you're going to use something called a separating funnel, right? So I'll draw one of those. Right, a separating funnel is, it looks like a sort of fat burette. And it's got a tap on it, okay? And what you're going to do you are going to get to so this is you're going to get your crude mixture. This is going to be your cyclohexene on the top layer. And on the bottom layer, you're going to have H2O with some cyclohexanol dissolved in it. And the first thing you do, so you chuck that into the flask, this is called a separating funnel. So you put that in, and then you add some, like, wash with some water. In actual fact, rather than using water, you usually use like a sodium chloride solution, but it's mostly just water. So you put that in and you fill that up. So what you're going to end up with is and you give it a good old shake, okay? And when you shake it, what happens is, so this is all water layer in here, and this is your cyclohexene in the top layer. When you shake it, it lets all of any cyclohexanol impurity, okay, and any phosphoric acid that's left over there as well, or anything else, that will dissolve in the water layer. Why will that dissolve in the water layer? Well, because it forms H bonds, doesn't it? It's going to prefer going in there than staying with the cyclohexene. So you can probably guess what you're going to do next is you open this tap, and what happens is that meniscus is that, you know, all the bottom layer comes down. Eventually your meniscus is going to be down there by the tap, and you throw away all of the aqueous layer. And you throw that down the sink. But what you normally do is, of course, you collect it in a beaker before you throw it down the sink, in case all the cyclohexene comes out. You don't close the tap in time. So if you do that, it doesn't matter, because you just put it back in the top and do the thing again. Okay. When you're doing your shaking, actually, you have a lid. You put a lid in the top there. Do that in blue, so you can give it a good shake and lather. But before you open the tap, you've got to remember to remove the lid, because if you don't, it makes a vacuum and none of the stuff comes out, and people think, oh, the tap's blocked. The tap isn't blocked, it's because you've forgotten to take the lid off. So here, then you're going to end up with a, what you're going to get from this, then, you are going to end up with a much purer sample of cyclohexene. It's nearly pure, but it's got a little bit of H2O in it still. And you need to remove the H2O, particularly if you wanted to, so you need a very dry sample if you want to do an infrared spectrum, which you probably won't do at school, but if you did want to do an infrared, you have to get rid of all of the water. You remove the H2O by adding, number one, you add calcium chloride solution. So you wash with calcium chloride solution, just like you washed with the water before. Sorry about that, sneezing. And then you'll get rid of a lot of the water that way, but that's not good enough to remove all the water. And then what you need to do then is you need to add some anhydrous calcium chloride solid, and that will remove the last traces of water and leave the calcium chloride solid in the beaker for 24 hours, and that gets rid of all of the water. So, and then you've got a reasonably pure sample of cyclohexene then. Of course, what you should really do then to get it even purer is distill it and collect off the liquid that boils at the right boiling point. But I don't think you need to do that in the required practical, that very last step. Okay, so we'll leave that there.